calorimetry is how we measure heat in a chemical reaction, okay? And it is typically done in what is called a calorimeter. Okay, a calorimeter is like a vessel, okay? And it's a really well insulated vessel because you need to be able to measure the temperature change and the heat change that happens within the reaction. Okay, and so a calorimeter, they can be really, really technical and very expensive and very high tech. Or what we use, and typically people use for a low cost calorimeter, is 2 styrofoam cups. Okay, and it keeps it really well insulated. Okay, and it does, and put a lid on it. But in general, it keeps the heat from the surroundings or the anything from the surroundings from invading or changing the chemical reaction. And so we can do calorimetry experiments just very inexpensively using 2 coffee cups. Okay, and that's really it. So that's called a calorimeter. Okay, so in calorimetry, we're going to use a topic or use a variable called specific heat capacity. All right, and I want you to understand what this means. Specific heat capacity is the energy required, the energy that it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so it's the amount of energy that it takes to heat up 1 gram of your substance by 1 degree. Right, it's a certain amount of energy. So every different material, every element, every different material has its own specific heat capacity. So lots of different things have specific heat capacity. Okay, let me give you an example. The specific heat capacity of water, is 4.18 kilojoules per mole. Okay, it would take, not kilojoules per mole, kilojoules per gram degree Celsius. And so 4.18 is the specific heat capacity of water. If I was going to talk about like iron, do you think the specific heat capacity of iron or metals is going to be higher than 4.18 or lower than 4.18? Explain to me why you think that. I see a lot of people saying higher, but I want you to talk through it. Why do we think it would be higher? Is it easier to heat up metal? I think it is easier to heat up metal. Metal's a good conductor of heat and electricity, which means it carries heat and heat travels through it really well, right? We can heat the pan faster than we can heat the water, right? And so the specific heat capacity of metals is significantly lower, okay? But think about, just kind of give that an example in your head so you can think about that, right? Metal adapts to its temperature much more quickly than water. So metal not only heats up faster, but it also cools down faster. Right? It adapts to its environment much more quickly. Okay, the one underneath of it is called molar heat capacity. It means almost the same thing, but it's talking about raise the temperature of 1 mole of a substance by 1 degree. Okay, so we'll use specific heat capacity a little bit more often, so the S. All right, calorimetry says if 2 reactants at the same temperature are mixed and the resulting solution gets warmer, this means the reaction taking place is exothermic. This is a little bit tricky. Okay, if I have 2 reactants that I put into a vessel and the temperature of that surrounding vessel heats up, that means that the reaction itself is releasing heat into its environment, and that would heat up the system. Okay, if the vessel or the reaction system gets colder while that chemical reaction is taking place, that would mean the reaction is endothermic. It's removing heat from those surroundings. Okay. All right, here is just kind of an example of what our calorimeters will look like. So we're going to do an experiment with calorimeters. We're going to have some styrofoam cups. We'll have our thermometer. We're not going to need a stirrer, but we're going to look at heat changes between hot water, cold water, and we're going to have some hot metal we'll put in, and we're going to see the heat change of. So that's really what our calorimeter system will look like. All right, here is the big equation for calorimetry. Heat Q equals ms delta T. Ms delta T. Okay, this one needs to go on your equation sheet. This is looking at just how much heat is contained in some certain system. How much heat is contained in the system. So Q is heat, M stands for mass, and we're going to measure that in grams, like we always do, grams. S is called the specific heat capacity. That's what we looked at earlier. So S is the variable for specific heat capacity. And then delta T is change in temperature. Do you remember the specifics of that delta that we learned about last time? Final minus initial, right? So if we have a temperature change that goes from 10 degrees to 100 degrees, our delta T would be 100 minus 10. Okay, 100 minus 10. All right, so MS delta T. This is going to be the big one that we use a lot. It's going to go on your equation sheet. That's how much heat is found in a certain substance. At this equation right here, and the unit for specific heat capacity, how that came about. Okay, I want you to just kind of bear with me here for just a second while we look at this. The unit for our specific heat capacity comes from this. If I was going to rearrange this equation to solve for S, Q is measured in joules, mass is measured in grams, and temperature is measured in degrees Celsius. So if I was going to rearrange my equation to solve for S, I would have to divide by grams and degrees Celsius. Grams and degrees Celsius. So that's where the unit comes from. The unit for S is joules divided by grams times degrees Celsius. Do you see where that comes about? Unfortunately, there's not like a nickname for that unit. Okay, the specific heat capacity has that unit because of the way the equation is derived. Right? If I would move those things around just to solve for S. So that's where that unit comes from. That means that in order for this equation to work, those units all have to be true. We have to have our mass in grams. We have to have our temperature in Celsius. Okay, when you did gas laws, you always had to convert your temperature to Kelvin, didn't you? But these ones we can keep in Celsius. Okay, yeah. This next one is using the, I didn't change this right here, sorry. I don't know where my slide is wrong here. This needs to say molar heat capacity. Okay, so my slide was wrong there. So go ahead and fix that if that's on yours. This is when we're talking about the moles of substance. So this is the molar heat capacity. And this guy right here would change to moles. I just must have copied and pasted and not fixed that part. So I apologize about that. Okay, so these need to say molar. C is molar heat capacity. And this is mole. Molar heat capacity. We don't use this one as often, but yeah, go ahead.
What do you mean by moles of substance?
Like it's a quantity of the substance. If I put in 58.5 grams of salt, that's 1 mole.
Okay.
Right? So it's talking about what's the molar mass of our substance tells me how many grams is in 1 mole of that substance.
Okay, so if it were
so it's a quantity.
Mole, it'd be like half the grams.
Exactly.
Okay.
Yep. So moles is just like a quantity value.
That's right.
Okay. All right, here we're going to just try some problems here. All right, it says how much energy, or in this case heat, is required to change the temperature of 50 grams of water by 15 degrees. The specific heat capacity of water is 4.18 joules per gram degree Celsius. Let me back up one second here. I want you to look. Mass was 50 grams. Delta T is 15 degrees, right? It says it's raised. Let me ask you one question. What if it had said the temperature was lowered by 15 degrees? It would just be a negative delta T, right? Very good. So our heat value can be negative. That would mean it's flowing outward, right? It's cooling off. Does that kind of make sense? Do you see how those go together? Okay, so what did we get when we solved for our Q value here? 3135. Yep, 3,135. And what's the unit that goes with heat? Joules. Very good. Very good. Tell me what questions we have with that. Okay, seem good enough? Joules goes with that. All right, this specific heat capacity for water we can put on our equation sheet because we're going to use it often.
Are
Okay.
you going to want that in kilojoules, or is that fine like that?
Just like this is fine. All right, what is the final temperature after 840 joules is absorbed by 10 grams of water at 25 degrees Celsius? Okay, so let's walk through some context clues here. Final temperature, that means I'm solving for TF. I'm going to go ahead and make that my question mark. Okay, I like to kind of make a list of my variables so I have an idea of what I'm looking for here. 840 joules. What value does that tell me? Q, right? 840. And it says it's being absorbed. So is that into or out of? Into. So it's a positive 840, right? We know that's positive. 10 grams of water. So my mass is equal to 10 grams. And what do I know about the specific heat of water? It's 4.18. And it says at 25 degrees Celsius, that has to then be my, what temperature?
didn't know to use it.
Initial. Yep, we're always going to use MS delta T. That's pretty much what we use 99% of the time. Yep. Okay, so initial temperature is going to be 25. So now I'm just going to plug in, right? 840 equals M times S times TF minus 25. Okay, do we feel comfortable with the algebra now to get that TF by itself? Yeah? Why don't you go ahead and solve that and we'll see if we match, and if we need to walk through the algebra, we can do that. All right. Let's try this one. If 12 grams of NaOH is added to 50 grams of water and the temperature rises from 25 degrees Celsius to 29 degrees Celsius, the specific heat of the solution is 3.90. What is the heat of the solution? Okay, so this says these are added together. So tell me, I want to look at this specifically. It says the specific heat capacity of the solution is 3.90. So are we going to evaluate the heat of these separately, or are we going to evaluate the heat of them together? Together, because solution insinuates that they are mixed together. Okay, so that means the specific heat is 3.90, and that means the mass of our system then is what? 62, right? We're going to consider them together. They are now one, right? They have become one. Temperature final is what? 29, and temperature initial is 25. Okay, so Q is equal to M times S times delta T. And could I do 29 minus 25 in my head and plug in 4? Absolutely, right? You can go ahead and speed that process up. But if you like to list them out and then put them in here, that works perfectly fine also. Yes.
Oh, never.
I got around here 967.2 joules. Are we in the ballpark there? So far, we've evaluated the heat in one component, right? A contained system. In our next problem, we're going to look at what happens when heat transfers from one item to another, okay? So this next question says you have a styrofoam cup with 50 grams of water at 10 degrees Celsius. I add a 50-gram iron ball that's heated to 90 degrees Celsius. So I'm putting something hot in the cup. We have the specific heat of water given and the specific heat of iron given. Calculate the final temperature of the water. Now, I want to talk about a couple things here. When we say final temperature, that means when these two things have come to what we call equilibrium. Do you know what equilibrium means? The heat transfer has stopped at that point because they've reached a place where the heat in both of these objects are equal. Okay? Think about if I leave a glass of ice water out for long enough. Eventually, what temperature does it come to? Room temperature. That's equilibrium. It is in equilibrium with its surroundings. And so we can have equilibrium contained within this system too. Once enough heat has flowed from iron to the water, it will reach an equilibrium temperature, right? And then if we remove the lid, it will become now in equilibrium with the room at some point. Does that kind of make sense? All right, so equilibrium just means when the heat transfer has stopped, right? There's been enough of a heat transfer and it stopped. So give me a range of temperatures here that we think our equilibrium could be. Because when it says find the final temperature of the water, we realistically mean it's going to be the final temperature of the water and the iron. They will both have the same final temperature. So we might even want to write this, right? Final temperature of the water and the iron. Because they are both going to be the same temperature. They're going to be at equilibrium. So what do we think? What's the range of temperatures it's going to be between here?
Like 50 degrees.
Okay, even a wider range. What does it have to be? It's got to be between 10 and 90, right? Sometimes we do the problems and we get wrapped up in the math and we get a final temperature of 137. Like, that can't be true, right? There's no way that our water can end up hotter than our metal originally was, right? So don't get wrapped up in the math and just assume like, well, this is what I got, so this is what it has to be, right? You're going to have a range of values here, okay? So the way we set these problems up is we look at this system right here. The heat gained by one of my systems is equal to the heat lost by our other system, right? This is the law of conservation of energy here. Whatever heat is flowing out of the metal must be absorbed by the water, right? It's not going to nowhere because we were going to have a contained system, right? We're in a calorimeter with our lid on. So the heat should stay in the water. And so this is the equation that we set up. The heat gained is equal to the negative heat lost, right? The heat that's flowing out. So when we set this up, if we expand this out, it's essentially this. MS delta T is equal to negative MS delta T, right? If you want to put this on your equation sheet, you could. This would be for calorimetry problems that are with two substances, okay? The negative here is really important. It's forgotten a lot, okay? All right, the negative is the negative should go on the side that starts out hotter. Right? It should go on the one that's losing the heat. So in this case, the iron side would get the negative. Okay? So let's go ahead and start plugging in our numbers here and let's see what we get. Let's make the left side of our equation the water side. We'll just keep this side the water for this problem and this side the iron. So the mass of our water is 50 degrees. Specific heat of water is 4.18. Temperature final, we don't know, and our initial temperature is 10. All right, on the other side, our iron, remember we have to include the negative. Our iron is 50 grams. Specific heat of iron is 0.45. We don't know our final temperature, and our initial temperature is 90. Okay, let's take a step back and let's make sure we're checking our math here. If our temperature, we know for the iron is going to go down. So no matter what I put here, this value is going to come out negative, right? And so that's why this negative needs to be here, because I want to make sure that it's going to end up, as we want our final temperature to be positive, hopefully, okay? All right, so let's go ahead and start doing the math here. We just need to basically get to where we combine our like terms. You're going to have to do some algebra here, most likely distributing them through. Do we need to walk through that algebra, or do you feel comfortable with that? If it were me, I would distribute. I don't know if it's called FOIL, or I don't know what the name for it is, but I'm going to distribute this, and then I'll distribute that, and then I'll start combining my like terms. Does that make sense or no? All right, I'll work up here. You keep working. If you want to watch what I'm doing, I'll have it up here on the front. So I'm going to take 4.18 times 50. That would make it 209 TF. And then I'll take 50 times 4.18 times 10. That gives me 2,090. Okay, on the other side, I get negative 22.5 TF. And this will be plus 2,025 because of these two negatives. Right, when we multiply that together, that's what's going to give me that plus sign. This one right here. So I distributed, if I multiply these two together, I've got some number outside of this set of parentheses, then I have to distribute it through there. Right? So 50 times 4.18 is 209. Yeah. And so then I need to take 209 times what's inside the parentheses there. So that's why I got 209 TF, and I got 209 times 10 is 2,090. Does that make sense? Yeah. Okay. So I did the same thing on both sides. Do we feel comfortable with how that distributes through there? I think it's called the distributive property. Does everyone feel comfortable with that? Once we're to this point, we combine like terms, right? We're going to combine our like terms, which means I would add 22.5 TF plus 22.5 TF. That gives me, gives me 231.5 TF equals, and meanwhile I need to move this to the other side, plus 290 plus 2090. That gives me 4,115. So now I would divide this over to get TF by itself. And I get final temperature equal to 17.78 degrees Celsius. Why is the temperature so much closer to 10 than to 90 if they are both 50 grams, right? We put in equal masses of both. Why is the temperature so much closer to 10 than it is to 90? That's right. The specific heat capacity of water is like, what, 10 times that of iron. So it takes a lot more energy to heat up water than it does heat up iron, okay? And I think that we would understand that in real life, right? I think that we see that being true, okay? All right, we feel good? Why don't you try this one on your own? This one's very similar. It says a cup containing 100 grams of water at 90 is mixed with a cup of 500 grams of water at 10. What's the final temperature of the water? Okay, see if you can give yourself maybe a range that you're thinking of, right? Look at the ratios here. See if you can figure out where you think our final temperature would be, and then let's try that one on your own. All right. Specific heat capacity of them is both 4.18, aren't they? Because it's both water. So if you have that on both sides, what could you do with it? Cancel it, right? It'll just speed up your math a little bit.
Wait, where do we put the 4.18?
I know that's what I did. Yeah, I didn't.
I even need it for this problem since it's both water.
Right, it's going to go on both sides,
So I don't need
but I just canceled it.
Yeah.
Yeah.
I think I need it since we're.
Who is heads? Who is heads?
I know how to do it. I just didn't know what the number was. I was close, but I wasn't right.
I knew exactly what.
Oh.
Actually,
I don't know. I don't think you were. Okay, so I didn't.
Oh, well.